In this video, we look at two more or three more examples of functions involving parameters where we're trying to achieve a certain goal. Okay, in this problem number 32, we're asked to find a function of this particular form, okay, where a and b are some parameters. We don't know what they are, but they are positive numbers. They're bigger than 0. And we want to find values of a and b so that we achieve the goal that the function y has a horizontal asymptote at y is equal to 5. Okay, so we're looking for a function of the form a times 1 minus e to the negative bx, and we want to figure out what the values of a and b are so that this function, right, has a horizontal asymptote at y is equal to 5, which means that figure out what a and b are so that this function will eventually approach the value y is equal to 5, something like this. All right, so take a moment to see if you can figure out what an example of a and b are, and then we'll come back. All right, so if you've had a chance to get a value of A and B, we'll go through that now. And if you haven't, pause the video again and try to keep working. But maybe here's an example of something to notice that since B is positive, then e to the negative bx is going to get closer and closer to 0 as x gets bigger to infinity. So that means that this term is going to go away, e to the negative bx, so long as b is bigger than 0. So that means that the function y is going to get closer and closer to a as x gets closer to infinity when b is a positive number. So hopefully that will help you figure out what an example of a and b would be. I'll give you a moment to write that down. So in my opinion, I would choose a is equal to 5 because that's what we want the y value to get closer to, and you can choose any value of b so long as it's bigger than 0. Okay, so if we test that now, here is our function y of f of x is equal to a times 1 minus e to the negative bx, b times x, sorry. And let's add a slider for all those things. And if a is equal to 5 and b is equal to 0.5, then this function does in fact have a horizontal asymptote at 5, and I just chose b is equal to 0.5, but any value of b, so long as it is positive, will have achieved that goal. Don't choose b negative because then you won't have a horizontal asymptote at 5. Right? So there is an example of another function, okay, that has a where the parameters can be chosen to achieve a certain goal. Okay, here's another example. Okay, to find a function of the form this, which has a local maximum at the point 0, 3. Okay, so let's take a look at this example. Let me clear out Desmos here. Let's take a look at what a function like this might look like and then figure out what does a and b have to be, or what could they be, so that this function, okay, has a local maximum. What can a and b be, so to speak, so that we have a local maximum at the point x is equal to 0 and y is equal to 3. So let's take a look at what this a possible function could look like. Right? So we could have f of x is equal to b multiplied by the exponential function negative x minus a. We need to square that and then divide the whole thing by 2. Okay? And A and B are parameters, so we want to add a slider bar for them. And here is our function, what that function looks like for A is equal to 1 and B is equal to 1. If you change B, we can see that the function is getting taller. So we wanted the maximum to occur at a value of x is equal to 0, y is equal to 3. So it looks like I need this function to get taller and taller until it hits 3. But this maximum is occurring at 1, 3. So I need to maybe change the a value, and the a value makes this graph move to the left and right. And so here, looks like a is equal to 0, b is equal to 3 will help me have a function that has a maximum at 0, 3. So that is just the Desmos graph to kind of play around with the parameters to get the answer. Let's see if we could do the math behind this now. Okay. So what we're going to need is the function, which we have, and we'll need the derivative of that function, which would be b is a constant multiplied by the derivative of e to the negative x minus a squared divided by 2. So I need the derivative of this function, but that is an exponential function, so the derivative is, you have to rewrite the function. But there's the chain rule, so we need the derivative with respect to x of the inside function. Right? And so the derivative of this inside function is, let me see, negative 2 times x minus a to the first power, and then the derivative of the inside function x minus a is 1. So our derivative for this problem is the 2's cancel, negative b times x minus a multiplied by e to the negative x minus a squared over 2. Okay. And so what we're doing is we're looking for that when that derivative is equal to 0. Okay. But one thing that we notice is that e to the negative x minus a squared over 2, that this is never equal to 0. This exponential function never equals 0. Negative exponentials always look like this, and they get closer and closer to 0. This is e to the negative kx. They get closer to 0 but never equal to 0. So the only way this derivative right here is going to be equal to 0 is if negative b times x minus a is equal to 0. But we know that to get this maximum to occur, right, b has to be something non-zero. B has to be greater than 0. Okay. We know that to get this maximum to be 3, y evaluated at 0 is supposed to be equal to 3. Okay. So that means that b is going to have to be a positive number. So if b is positive, that means that x minus a is going to have to equal to 0, which means that x is going to have to equal a. And that is our critical number now. So when we create a critical number, a sign line for f prime, when x is equal to a, that is our critical number. Okay. And this derivative right here, y prime, right? Y prime, the sign of it is going to be depending on negative b times x minus a. Okay. B is going to have to be positive, and when x is bigger than a, right, you'll look at negative b times x minus a. If b is positive, negative b is a negative number, and when x is bigger than a, when you test this point, x minus a is positive, negative times positive is negative. Okay. And if b is positive and x minus a is negative, because x will be less than a, you'll get a negative times a negative, which will make it positive. So what we're seeing here is that we have to have a local maximum at x is equal to a, whatever that value of a is. And because we want the maximum to occur at 0, 3, and the local maximum occurs at x is equal to a, that means that a has to be equal to 0. Okay? And when a is equal to 0, we know that our function is going to now be of the form y is equal to b multiplied by e to the negative x squared over 2, because that's when a is equal to 0. And because we want the critical value to occur at 0, 3, when you put in 0 for x, at x is equal to 0, this will tell us that y has to be equal to b. And we want that y value to be equal to 3, so that means that b has to equal 3. So there is another example with dealing with taking derivatives again, creating a sine line, and figuring out that no matter what the values of a and b are, we're always going to have a local maximum at x is equal to whatever the value of a is. When a is equal to 2, you'll get a local maximum at 2. A moves this graph left and right. B changing doesn't change the fact that we have a local maximum. All it does is it changes where the y value of where that local maximum occurs. So B changes just the height of the maximum value. So when A is equal to 0 and B is equal to 3, that gives us the function that we were hoping to achieve.